Steel. It's the backbone of modern civilization. From skyscrapers scraping the sky to bridges spanning mighty rivers, to the very car you drive and the appliances in your home, steel is everywhere. And behind every ton of steel lies an incredible industrial journey that begins with something raw, rough, and earthy: iron ore. But how exactly is iron ore transformed into steel on a scale of millions of tons every year? Today, we'll dive deep into the supergiant steelmaking process. Inside massive factories and production lines where chemistry, physics, and engineering come together in one of humanity's greatest industrial achievements. Before we jump into the furnaces, don't forget to hit that subscribe button and ring the bell. Steel production starts far away from the city, in rugged landscapes where miners dig deep into the earth to extract iron ore. The United States, Brazil, Australia, and China are global leaders in iron ore mining. Iron ore isn't pure iron. It's a rock rich in iron oxides like hematite and magnetite. These ores often contain 50 to 70% iron, making them ideal for industrial use. The mining process begins with blasting and drilling. Giant drills bore holes into the earth, explosives loosen massive chunks of ore, and gigantic haul trucks, some weighing over 400 tons, carry it to crushers. Once crushed, the ore is screened and separated. The fine particles are washed, magnetically sorted, and prepared for transport. Every year, more than 2.5 billion tons of iron ore are mined globally, feeding steel plants across continents. Raw ore alone isn't good enough for efficient steelmaking. It needs processing. This stage is called beneficiation. At beneficiation plants, iron ore is ground into powder. Magnetic separators pull out the iron-rich particles while waste rock, called tailings, is discarded. To make handling easier, the fine ore is then rolled into marble-sized balls called pellets. Pellets are a steelmaker's favorite. They're uniform, easy to transport, and provide consistent quality inside blast furnaces. Every year, pellet plants produce hundreds of millions of tons, each pellet a small but essential piece in the global steel puzzle. Now comes the heart of the process, the blast furnace. Standing over 100 feet tall, these industrial giants have been in use for centuries but have grown unimaginably efficient today. Inside, three main ingredients go in: iron ore, or pellets, coke, and limestone. Coke is carbon-rich fuel made by heating coal without oxygen. Limestone helps remove impurities, and iron ore provides the metal. The furnace is charged from the top with alternating layers of these materials, while hot air up to 2000 degrees Fahrenheit is blasted from the bottom. Inside, a chemical dance unfolds. The coke burns, producing carbon monoxide, which strips oxygen away from iron ore, leaving molten iron. Meanwhile, limestone combines with impurities to form slag, which floats on top of the liquid iron. Every day, a single blast furnace can produce 10,000 tons of molten iron, also called pig iron. This glowing orange-hot liquid is the foundation of steel. Pig iron is strong, but it's brittle and filled with carbon. To turn it into steel, we need refinement. Enter the basic oxygen furnace, BOF. In this massive converter, pig iron is poured in along with scrap steel, recycled from old cars, appliances, and construction. Then, pure oxygen is blasted through at supersonic speed. The oxygen reacts with carbon, silicon, and phosphorus, burning away impurities in minutes. What's left behind is refined liquid steel. strong, flexible, and ready for the modern world. A single BOF can turn 300 tons of pig iron into steel in less than an hour. Compare that to centuries past, when steelmaking was slow, small, and costly. This scale is nothing short of revolutionary. Now that we have molten steel, it needs to take shape. Through continuous casting machines, the glowing steel is poured into water-cooled molds. As it flows downward, the outside solidifies while the inside remains molten. The result? Long, continuous slabs, blooms, or billets of steel. These can weigh up to 40 tons each and stretch dozens of feet long. Unlike old ingot casting methods, continuous casting saves energy and time while improving quality. The slabs and billets are still rough. To transform them into products we recognize, they head to the rolling mills. Here, steel is reheated to over 2,000 degrees Fahrenheit and squeezed between massive rollers. The pressure flattens and stretches the metal into desired shapes. Thin sheets for car bodies and appliances, long rails for trains, structural beams for skyscrapers, wire rods for machinery and electronics. Some rolling mills operate continuously for miles, turning glowing red slabs into paper-thin steel sheets in minutes. Steel doesn't stop at rolling. To enhance performance, it undergoes finishing processes. By the end, steel is tailor-made for thousands of industries. Here's something incredible. About 90% of steel is recycled. Unlike plastic or paper, steel can be melted and reused endlessly without losing strength. Scrap steel goes back into furnaces, reducing the need for raw ore and saving huge amounts of energy. In fact, recycling steel uses 75% less energy than making it from scratch. This makes steel not only the most widely used material, but also one of the most sustainable. Globally, steel production exceeds 1.9 billion tons annually. China alone makes more than half of that. In the US, production exceeds 80 million tons a year. This steel becomes the backbone of $2.5 trillion worth of global industries: construction, automotive, shipping, energy, and beyond. And that's how millions of tons of steel are made every year in massive production lines that keep our world standing tall. Thanks for watching. If you enjoyed this journey into the world of steel, don't forget to subscribe, leave a like, and share this video. We've got more amazing stories from the world's most mind-blowing industries coming your way. Have you ever held a sapphire in your hand? That brilliant blue stone sparkling under the light isn't just a gem, it's the product of millions of years of nature's work and decades of human effort. Today we're taking you deep inside the world of supergiant sapphire mining, from rugged mountains in Montana to cutting-edge processing facilities, to see how one of the world's most valuable gems is found, extracted, and transformed into treasures that last for generations. Before we dive in, don't forget to like, subscribe, and hit that notification bell for more fascinating behind-the-scenes journeys of how the world's most valuable materials are made. Sapphires aren't just beautiful stones. They're a type of corundum, a mineral made of aluminum oxide, and they rank 9 out of 10 on the Mohs hardness scale, just under diamonds. What makes sapphires special is their trace elements. Tiny amounts of iron and titanium give them that deep, royal blue color. Other trace elements can make them pink, green, yellow, or even colorless. In the US, the most famous sapphires come from Montana, a state often called the Treasure State. Here, sapphires were first discovered in the 1860s by gold miners. They weren't looking for gemstones, they stumbled upon them while panning for gold. But soon, sapphire fever spread. By the late 19th century, the famous Yogo Gulch deposit was discovered. Yogo sapphires are legendary, prized for their uniform cornflower blue color, exceptional clarity, and the fact that they don't need heat treatment to enhance their beauty. From royal crowns in Europe to engagement rings in the US, sapphires have always carried an air of mystery, wealth, and prestige. Imagine standing in the wide-open landscapes of Montana. Rolling hills, gravel bars along the Missouri River, and rugged gulches carved by ancient glaciers. This is sapphire country. Sapphires are typically found in placer deposits, where ancient rivers carried them down from eroded mountain rocks. Over time, the heavier sapphires settled in gravel beds, waiting to be discovered. To locate sapphire-rich areas, geologists study the land, analyzing sediment layers and rock formations. In modern mining operations, giant excavators and dredging machines are used to scoop up tons of gravel and sediment. Every shovelful could contain sapphires, but the odds are small. On average, miners might move hundreds of tons of rock to find just a handful of quality gems. That's what makes sapphire mining both a gamble and a wonder. Now let's head inside a supergiant mining plant. Massive bulldozers dig up sapphire-bearing gravel, sometimes working through layers that are millions of years old. The raw gravel is loaded into washing plants. High-powered water jets separate lighter material from heavier stones. Sapphires, being heavier, settle at the bottom along with other dense minerals. Workers and machines sift through the concentrate, looking for flashes of blue, green, or yellow, the telltale sparkle of a sapphire. The excitement of finding a sapphire hasn't changed much since the gold rush days. Each discovery feels like unearthing a hidden star from the earth. A rough sapphire doesn't look like the sparkling gemstone you see in jewelry stores. It's often cloudy, irregular, and dull. Here's how it's transformed. Grading. Experts examine the rough stone for color, clarity, and size. Cutting. Skilled lapidaries use diamond-tipped saws and precision machines to cut the stone. The goal: maximize brilliance while minimizing weight loss. Polishing. Facets are polished to perfection, unlocking the sapphire's fire and sparkle. Heat treatment. Optional. Some sapphires undergo controlled heating to enhance their color. But remember, Yogo sapphires from Montana are naturally beautiful and rarely need treatment. The result? A gemstone that can fetch anywhere from a few hundred to tens of thousands of dollars per carat. While sapphires are famous in jewelry, did you know they also power modern technology? Industrial sapphire glass. Scratch-resistant, used in watch faces, smartphone screens, and scientific instruments. Laser technology. Sapphire crystals doped with titanium create powerful blue lasers. Electronics. Thin sapphire wafers are used in semiconductors and LED manufacturing, so sapphires aren't just about beauty. They're also about science and progress. Behind every sapphire is a story of people. In Montana, mining towns grew around sapphire deposits. Families worked the gravel bars together, passing down stories of luck and discovery. Lapidaries, the skilled craftsmen who cut and polish gems, dedicate years to mastering their art, turning rough stones into dazzling treasures. Jewelers and designers then carry the final product to customers around the world, where sapphires symbolize love, loyalty, and wisdom. Mining also brings challenges, balancing economic opportunity with environmental responsibility. Modern operations focus on land restoration, water recycling, and sustainable practices to protect Montana's natural beauty. Think about this. A sapphire you might see in a ring today could have formed over 500 million years ago, deep within the Earth's crust. From its birth under extreme heat and pressure, to its discovery in a Montana gravel bed, to its transformation in a cutting workshop, that journey is nothing short of extraordinary. Thanks for watching, and until next time, keep discovering. Beneath the Earth's crust, hidden in ancient volcanic formations, lie some of the most prized treasures known to mankind. Diamonds. For centuries, these shimmering stones have captivated royalty, industries, and investors alike. But their story begins long before they ever reach a jeweler's display. The history of diamond mining stretches back over 2,500 years to ancient India, the first known source of diamonds. These early gems were found in riverbeds and traded along the Silk Road, believed to bring strength, invincibility, and spiritual clarity. By the 18th century, Brazil had become the world's largest supplier, before the discovery of massive deposits in South Africa changed everything. In 1867, a young boy found a shiny stone along the Orange River, a 21-carat diamond that sparked a modern diamond rush. This led to the founding of some of the world's most famous mines, including Kimberley, home to the legendary Big Hole. Today, diamond mining is a high-tech global enterprise. The world's largest mines span across continents, from Jwaneng in Orapa in Botswana, to Mirny in Russia, Venetia in South Africa, and Diavik in Canada. Some operations reach depths of over 1,000 meters, and each year, more than 130 million carats of rough diamonds are produced globally. But how are these tiny crystals of carbon extracted from solid rock? And what does it take to bring them from the Earth's core to the world's most exclusive boutiques? Join us as we journey deep into the heart of modern diamond mining, a world of massive machines, precision science, and sparkling ambition. Geologists use satellite imaging, geophysical surveys, and soil sampling to identify promising sites. Once a potential kimberlite deposit is located, it's drilled and sampled to assess the concentration of diamonds. This process can take years and millions of dollars in investment before a mine is approved. Only a small percentage of kimberlite pipes actually contain diamonds in commercially viable quantities. If one does, the project moves into the development phase. In open-pit operations, huge amounts of overburden, layers of soil and rock, must be removed. The process begins with explosives, followed by massive hydraulic shovels and dump trucks that can carry up to 400 tons of rock at a time. This material is hauled to the primary crushing stations, where the hard kimberlite rock is broken down to manageable sizes for further processing. Once the ore is brought to the surface, it enters the primary crushing phase. Here, giant jaw crushers reduce large rocks into smaller pieces. The material is then passed through secondary and tertiary crushers to reduce it even further. By now, it resembles gravel-sized particles. The goal? To liberate the diamonds trapped within the rock matrix. From here, the crushed ore is sent into a washing and screening circuit to separate fine particles and slurries. These finer materials are essential because diamonds are often only a few millimeters in size. Next, the slurry moves through dense media separation tanks, where materials are separated based on their density. Since diamonds are extremely dense, they sink to the bottom, while lighter waste material floats. The diamond-bearing concentrate is now ready for recovery, but finding these tiny gems in tons of rock still requires a highly specialized process. Now, the real treasure hunt begins. The diamond-rich concentrate is fed into X-ray fluorescence machines which detect the unique light refraction of diamonds. When a diamond is identified, a jet of compressed air precisely ejects it from the conveyor belt into a separate container. This method is remarkably effective, recovering over 98% of diamonds in a single pass. Recovered diamonds are still raw and coated in grime, they undergo acid cleaning to remove any residue from surrounding rock. At this stage, they're referred to as rough diamonds. Next, the diamonds are hand-sorted into various categories based on size, shape, color, and clarity. This step is done by trained gemologists who evaluate thousands of stones each day.